Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. Usually when we talk about engineering, there's this underlying assumption, almost like a comforting blanket, of absolute precision.
Oh, yeah. The illusion of the perfect equation.
Right. Because we're taught from our very first university physics class that the universe operates on solvable equations. I mean, you have a physical load on a steel beam, you calculate the stress, you look up the material properties to find the yield point, and the math just points a definitive finger and says, there is your safety factor.
It's clean. It's totally binary.
Exactly. Safe or unsafe, broken or not broken.
And that is the dream we all want to live in, right? We crave that visibility. We want every single aspect of the physical universe to fit neatly into our carefully formatted spreadsheets. But the moment you step out of pure static mechanics and you wade into the world of reliability, prediction, and failure rates...
Oh, man, it just falls apart.
It shatters. That pristine mathematical machinery just shatters. You are suddenly navigating a landscape defined entirely by uncertainty, these statistical ghosts, and really diagnostic muddy waters.
Which brings us to today's mission. We are taking a massive stack of sources today. We've got articles, historical data, research papers on statistical inference, and we're doing a deep dive into the messy, misunderstood, and frankly, incredibly frustrating world of reliability prediction.
It's a massive pain point for so many teams.
It really is. We are looking directly at a pain point I know you, the listener, have felt in your bones. You're sitting at your desk, you design what you think is a flawless system, you run the numbers, and the math swears up and down that this mechanical valve or, this electronic control unit will last for a decade without a single hiccup.
And then you ship it.
You ship it, and 6 months later, it fails catastrophically in the field.
Yeah.
And you are left staring at your screen just wondering what went wrong. Did manufacturing mess up? Did the customer abuse it?
Well, most of the time, I hate to say it, the failure wasn't a fluke of the universe. The failure happened because the way engineers are taught to interpret failure rate data is it's fundamentally flawed from the ground up.
Wait, flawed how? Like the math is wrong?
No. The flaw is almost never in the actual arithmetic you did. You probably carried the one and divided perfectly correctly. The trap lies in the philosophical interpretation of what those database numbers actually represent.
Ah, I see.
We have this collective industry habit of treating statistical probabilities as if they are hard physical laws. And they just aren't.
So today we are breaking down the biggest real-world issues you run into. We are calling out the deadly misconceptions that keep ruining designs, and we are going to build a step-by-step approach to actual, practical optimization. So you can stop designing for a fantasy and start designing for reality.
That's the goal. Let's start at the very beginning of the design phase.
All right, before we even touch a calculator, we have to look at where our numbers actually come from. Because treating a failure database like a universal truth is, it's like trusting a car's estimated highway miles per gallon rating while you're driving up a mountain, towing a boat in an absolute blizzard.
Yeah, the environment and the operator change the fundamental reality of the machine. The origin of the data is everything.
So let's talk about those origins. Where do engineers usually get these numbers?
Traditionally, engineers lean on a few heavy-hitter databases.
Yeah.
These are massive volumes of historical data that have shaped reliability engineering for decades now.
Like the military handbooks.
Exactly. The granddaddy of them all is the U.S. MIL-HDBK 217. This is the famous military handbook for electronic failure rates. It uses incredibly complex regression models based on, part complexity, junction temperature, the operating environment, packaging.
Right.
But what is really fascinating about MIL 217 is that if you track its successive issues over the years, the published failure rates keep dropping. They get lower and lower.
Well, my first instinct is to say, that's just because the technology is getting better, right? I mean, manufacturing processes improve, clean rooms get cleaner, so the components themselves are genuinely more reliable.
And that is certainly part of it. Better manufacturing and more rigorous screening definitely play a huge role. However, it is equally likely that they simply reassessed their earlier data and realized they were being wildly pessimistic.
Oh, interesting.
Yeah, early reliability data often included failures that weren't actually the component's fault at all. Either way, it demonstrates that this quote-unquote hard data is actually a moving target.
Okay, so that's electronics. What about mechanical stuff?
Moving away from electronics, you have NPRD 95. That's the Non-Electronic Parts Reliability Data Book. This is basically the Bible for mechanical, hydraulic, and pneumatic parts.
And how does that differ from the military handbook?
Well, Unlike MIL 217, which leans really heavily on mathematical models and theoretical stress formulas, NPRD 95 is grounded entirely in actual field data. It simply logs the number of recorded failures against the millions of operating hours in various real-world environments.
Okay, and then there is ARETA, right? The offshore reliability data.
Yes, ARETA is a big one.
When I look at the stakes involved with ARETA, it really puts everything into perspective for me because this database is managed by a consortium of massive oil companies. We are talking BP, Shell, Statoil, and they are tracking safety-related equipment in some of the most brutal environments on Earth.
Offshore oil rigs are no joke.
Exactly. Fire and gas detection systems, emergency shutdown valves, massive industrial compressors. If a part fails in an ARETA dataset, it's not a minor inconvenience. It's potentially a catastrophic environmental disaster or a loss of human life.
Right, and those extreme stakes dictate the rigor of the data collection. ARETA is incredibly specific because the oil and gas industry absolutely demands it, but the modern engineer rarely just looks at one single source anymore.
They use aggregators.
Exactly. The source material we are examining today heavily references Faraday Point 3. Think of this as a massive synthesis engine. It aggregates over 20 different data sources, including the ones we just talked about, and it provides synthesized ranges of failure rates for components.
And this is exactly where the illusion of precision shatters for the engineer who's just trying to build a reliable system.
Yeah.
Because you open Faraday, or you look up a standard component, say a commercial signal transformer, or a basic hydraulic check valve.
Yeah.
You want one number to plug into your reliability block diagram.
So give me the number, right?
Right. But instead, you see that the failure rates from these synthesized sources span one or two full orders of magnitude for the exact same component.
Which is terrifying. A variance of 2 orders of magnitude is staggering. It means one highly respected engineering source is telling you a part will fail 100 times more often than another equally respected source claims.
100 times.
Yes. So for an engineering manager trying to calculate a system's mean time between failures, or MTBF, to, guarantee a warranty period, that level of variance is paralyzing.
It makes the entire exercise feel like statistical astrology. If the baseline data has a 100-to-1 margin of error, how can anyone justify the cost of adding a redundant safety system? Why does this massive discrepancy even exist? Are the databases just poorly managed?
No, the databases are managed as well as they can be, honestly, but they're subject to 4 hidden variables that completely warp the data behind the scenes. When you just pull a raw number from a column, you are totally blind to these factors.
Okay, let's break these down. What's the first hidden variable?
The first hidden variable is the component source. This refers to the degree of screening and quality assurance applied before the part ever reaches the field.
Makes sense.
Imagine a standard integrated circuit. The one bought off the shelf for a cheap consumer toy relies on the exact same underlying silicon technology as the one bought for a deep space satellite.
Right, the silicon is the silicon.
Exactly. But the satellite part undergoes 100% environmental screening, intense thermal cycling, and factory burn-in testing.
So the weak links the parts with microscopic manufacturing defects.
Yeah.
Those were already thrown in the trash before the data collection clock even started ticking.
Precisely. So the space agency's data will show an incredibly low failure rate, while the toy manufacturer's data will show a much higher one, even though the fundamental component design is identical.
Okay, that's variable 1. What's the second hidden variable?
The second is circuit tolerancing, and this is entirely about the skill and the effort of the design engineer who integrated the part, because components rarely just explode or snap in half.
Right, they just age.
Yes, their internal parameters just drift over time, like a resistor's ohmic value might slowly increase. Now, if the surrounding circuit was designed to be highly tolerant, meaning it can still function perfectly fine, even if that resistor drifts by 10%, no failure is ever perceived by the user and nothing gets logged.
But if a lazy or rushed designer built a brittle, highly sensitive circuit, that exact same 10% drift causes the entire system to crash.
Yes.
And then the maintenance tech logs it as a quote-unquote resistor failure in the database, when in reality the resistor was just aging normally. The failure was a brittle system design, making a perfectly adequate component look terrible.
That happens constantly. The database doesn't know the circuit was brittle. It just tallies another tick mark against the resistor.
That's wild. Okay, what's the third factor warping the data?
The third is reliability growth. This is the positive feedback loop between field experience and the manufacturing line.
Like iterative improvement.
Exactly. Say a major telecom company tracks field failures of a router, they identify a specific weakness in a solder joint, and they update their manufacturing process. The batches produced in year 3 are inherently vastly more reliable than the batches produced in year 1.
Oh, I see where this is going.
Right. If a database indiscriminately mixes early lifecycle data with late lifecycle data, the resulting average is a completely misleading fiction. It represents neither the bad early parts nor the good late parts.
It's like judging a professional athlete's current skill level by averaging their stats from when they were a clumsy rookie with their stats from their championship year. It gives you a number that doesn't actually describe their current reality at all.
That's a great analogy. It completely flattens the reality.
Okay, so we have component source, circuit tolerancing, reliability growth. What is the fourth variable?
The fourth is perhaps the most insidious, and I'll tell you, it drives reliability engineers completely crazy. It is maintenance philosophy.
Maintenance philosophy, how does that warp the database?
Well, in many complex industries, when a massive system goes down, technicians do not have the time to sit there with a multimeter and find the exact microscopic point of failure. The factory floor is losing thousands of dollars a minute.
Right, the pressure's on to get the line moving.
Exactly. So they use trial and error replacement. It's often called shotgun maintenance. The system stops, so they just swap out circuit board A. They turn it on. Still broken. They swap out circuit board B. It works. The line is back up.
Oh man, let me guess. The technician fills out the paperwork and writes down that both board A and board B failed.
Yep. They both get logged as replacements, which data scrapers almost always interpret as failures. Board A was probably in perfect working condition. It was just a victim of diagnostic guessing.
But now, the database has artificially inflated the failure rate of board A.
In some systems, this artificially inflates failure data by absolutely massive amounts.
So if I am sitting at my drafting table and I know that these databases are polluted by diagnostic guessing, brittle circuit designs, and vastly different screening processes, why do we even open these books? I mean, if the data is this muddy, aren't we just guessing?
We use them because we have to anchor our designs to something, but we have to radically change how we view that anchor. A component failing in the field is a system-level event. It is deeply related to the component itself, sure, but a massive proportion of field failures are actually due to software edge cases, human operators doing things they shouldn't, unforeseen environmental interference, or multiple components drifting simultaneously in ways the designer didn't anticipate.
So the data is just a hint.
The data from MIL 217, or ERATA, is a guide. It is a relative indicator of risk. It is not an absolute legally binding guarantee of how your specific design will behave in the real world.
It's a compass, not a GPS with turn-by-turn directions.
Yeah.
It points you toward north, but you still have to navigate the rocks yourself.
That is the perfect way to look at it. It tells you the relative contribution of different parts to your total failure risk. It tells you that a complex mechanical relay is inherently riskier than a solid-state piece of silicon. But taking a raw number from a table and treating it as a sacred promise to your customer is a fundamental, dangerous error.
Okay, let's say we accept that reality. We accept that the data exists in these massive, terrifying ranges. We are looking at a factor of 50 to 1 between the highly optimistic telecom data and the deeply pessimistic military data. But at the end of the day, I still have to pick a single number to plug into my reliability block diagram to see if the system works.
You do.
And this brings us to a massive mathematical trap that catches so many engineers off guard. The averages trap.
It is a classic trap, and it stems from a basic misunderstanding of how human intuition fails when dealing with statistical orders of magnitude.
Let's set up this scenario. I'm looking at my database range. The most optimistic source says my hydraulic valve has a failure rate of 0.1 per million hours.
Okay.
And the most pessimistic source says it's 1.0 per million hours. My intuition, and honestly the intuition of almost anyone who has ever taken a basic math class, is to just split the difference, take the arithmetic mean.
Which is what everyone does at first.
Right. You had 0.1 and 1.0, you get 1.1. Divide by 2, and you get an average failure rate of 0.55 per million hours. It feels fair. It feels safe.
It feels logical right up until you look at what that arithmetic mean actually represents structurally. Think about the numbers. Your arithmetic mean of 0.55 is more than 5 times larger than the optimistic lower estimate, but it is only about half of the pessimistic upper estimate.
Wow. Okay. The center of gravity is completely skewed. It is heavily biased toward the larger number.
Yes. When your data range spans an order of magnitude or more, the larger value absolutely dominates the arithmetic mean. By using simple addition and division, you are essentially allowing the worst-case scenario to drag the entire prediction almost entirely into its own territory.
So you aren't really finding the middle.
Not at all. You are no longer designing for the average case. You are accidentally designing for a slightly mitigated worst-case scenario.
So what is the mathematically correct way to find the middle ground when the extremes are so far apart?
You have to use the geometric mean. Instead of adding the two numbers and dividing by 2, you multiply the two numbers together and take the square root.
Okay, so the square root of 0.1 multiplied by 1.0 gives you a geometric mean of roughly 0.316.
Exactly.
That feels like a subtle difference, 0.316 versus 0.55. But let's break down why 0.316 is a vastly superior representation of reality.
It is superior because the geometric mean averages the orders of magnitude rather than the raw linear values. Look at the proportional relationship. 0.316 is roughly 3 times larger than the optimistic estimate of 0.1.
Okay.
And the pessimistic estimate of 1.0 is roughly 3 times larger than 0.316. It sits perfectly in the proportional middle of the multiplier spectrum.
Oh, I see. It balances the ratio on both sides.
Exactly. When you are dealing with failure rates, which inherently behave logarithmically across different stress environments and quality levels, the geometric mean provides the most credible, balanced, and defensible baseline.
This makes so much sense. And it's exactly how the Faraday.3 database is structured to help engineers. It doesn't just give you the wild extremes, it provides data in 3 distinct columns: the minimum reported rate, the maximum reported rate, and the geometric mean.
Which is incredibly helpful.
Right, because if you are designing a system and you have no specific compelling reason to assume it will be abused in an extreme environment, or conversely, pampered in a hermetically sealed clean room, the geometric mean is your most mathematically sound starting line.
It is the only rational starting point. And once you have that geometric mean baseline, you then apply specific multipliers based on the reality your product will actually face in the field. The databases provide these modifiers.
Give me an example of a modifier.
Let's look at quality multipliers. If you procure a standard commercial off-the-shelf item, your multiplier might be 2.0. You take your geometric mean and double it, acknowledging the risk of lower quality control.
Makes sense.
But if you pay the premium to have those exact same items subjected to 100% screening and factory burn-in, your multiplier might drop to 0.4. You are drastically shrinking your expected failure rate because you've paid to weed out the weak links.
And the environmental multipliers are even more extreme, aren't they?
Oh, absolutely.
If your electronic component is going to live its life in a dormant situation, say sitting on a warehouse shelf or idling in a backup system, the multiplier is 0.1. You shrink the baseline failure rate to 1/10.
Because it's practically asleep.
Right. But if that exact same component is destined for a mobile ground environment, like being bolted to the rattling chassis of a military jeep driving over dirt roads, the multiplier is a massive 4.0. You are quadrupling the baseline rate just based on the vibration and thermal shock.
Exactly. You tailor the geometric mean to your specific reality.
Okay, I want to push back on this a little bit, or at least channel the anxiety of a lead engineer who is terrified of a product recall.
Bring it on.
If I am designing a mission-critical system, say a medical device or an aviation control, shouldn't I just use the absolute maximum failure rate from the database? I mean, if I use the geometric mean, aren't I designing for an quote-unquote average day when my ethical responsibility is to guarantee safety on the worst possible day?
That is a very noble, very common intuition, and if you follow it, you will destroy your own project.
Really? Destroy it?
Completely. Think about it. If you take the absolute worst-case pessimistic failure rate for every single resistor, capacitor, valve, and seal in a complex system, and you sum them all up, your predicted system-level failure rate will be so impossibly astronomical that the system will look entirely unviable on paper.
Oh, the math will tell management that the machine is guaranteed to explode the second you turn it on.
Precisely. And to counter that fake mathematical crisis, you will be forced to add ridiculous convoluted levels of redundancy. You will add backup pumps for your backup pod.
Which adds weight and cost.
Immense weight, staggering cost, manufacturing complexity, and ironically, it introduces entirely new, unforeseen failure modes. You end up over-engineering the system to death because you modeled a fantasy where every single component was simultaneously experiencing its worst possible day in history.
You essentially build a fortress when you only needed a storm shutter.
Beautifully said.
Oh.
You use the geometric mean because it represents the central tendency of a component's behavior across a massive, normal distribution of operational lives.
And you just scale up the parts you know will suffer.
Right. If you know for a fact that a specific subsystem is genuinely going to be pushed to its absolute thermal limits, you use the environmental multipliers to scale that specific subsystem up. But you never assume the maximum published database value as your starting baseline because, as we discussed earlier, those maximum values are heavily polluted by diagnostic replacements and brittle legacy designs.
Okay, that makes perfect sense. We have successfully navigated the database minefield. We know how to pick a realistic baseline using the geometric mean and targeted multipliers. We have our prediction on paper.
The easy part is done.
Right, because paper doesn't survive contact with the real world. Eventually, you have to build a physical prototype, put it on a test bench, and prove your numbers. And this is where we run into a psychological and statistical trap that ruins careers. Let's talk about the zero failure fallacy.
Oh, this is a big one. This is the arena where statistical inference clashes violently with common sense. Human intuition is terrible at statistics, and nowhere is that more obvious than in physical reliability testing.
Let's lay out the absolute basic math first. To get a point estimate of a system's mean time between failures and MTBF, the formula is wonderfully simple. MTBF is simply the total accumulated test hours divided by the total number of observed failures.
Very straightforward.
So if your company builds 10 prototype hydraulic pumps and you run each of them on a test bench for 1,000 hours, you have accumulated 10,000 total test hours. If 2 of those pumps break during the test, your math is 10,000 divided by 2. Your point estimate MTBF is 5,000 hours.
That is the raw point estimate. But here's the critical flaw in treating that number as gospel.
Okay.
If you walk back into the factory, grabbed 10 different pumps from the exact same manufacturing batch, and ran that exact same 1,000-hour test again, you almost certainly wouldn't get exactly 2 failures at the exact same time.
Right, you might get 1 failure, you might get 4 failures, you might get none.
Because of random sampling and the inherent chaos of physical variance, the only way to find the true absolute MTBF of a specific batch of pumps would be to literally run every single pump you manufactured until it physically broke.
Yeah, which is obviously a terrible business model, because then you have 0 products left to sell to your customers. They're all breaking in your lab.
Exactly. Which is why the entire field of reliability relies on statistical inference. We test a tiny sample, and we attempt to make a definitive statement about the entire untested population. But, and this is the rule that gets ignored, that statement must absolutely always be accompanied by a confidence level.
And this brings us to the 2 main types of tests: time truncated and failure truncated.
Let's define those real quick.
Sure, if you decide beforehand, we're going to run these pumps for exactly 1 month and then shut them off regardless of what happens, that is a time truncated test. If you decide we're going to run these pumps indefinitely until exactly 3 of them break and then we stop, that is a failure truncated test.
Right.
But let's look at the absolute most dangerous, intoxicating scenario for an engineering team. What happens when you test a component and you get absolutely 0 failures?
It is the moment every team cheers, and it is the moment the reliability engineer starts to panic.
Because the math breaks.
Yeah.
Say we run our 10 prototype pumps for 1,000 hours each. 10,000 total hours. None of them break. They run perfectly. We plug that into our simple MTBF formula. Total hours. 10,000.
Yeah.
Number of failures, 0. 10,000 divided by 0 is, well, mathematically it's undefined, but conceptually it's infinity.
Yes.
Does that mean the pump has an infinite MTBF? Have we invented a machine that defies entropy and will last forever?
Of course not. Every engineer knows it won't last forever. But without a firm grasp of statistical tools, management often looks at a 0 failure test report and assumes they have a near-perfect, bulletproof part. They assume the risk has been completely eliminated.
It reminds me of someone testing a bulletproof vest by firing exactly 0 bullets at it, observing that there are no holes, and declaring it impenetrable.
Exactly.
Or flipping a coin 0 times, watching it sit perfectly still on the table and assuming it will never ever land on tails. You haven't proven that the part won't fail. You simply haven't observed the inevitable failure yet. Your sample size and time is just too small.
That's spot on. To interpret a test with zero failures or any incredibly small number of failures, assuming we're dealing with a constant failure rate, we have to leverage the chi-square distribution.
The chi-square test.
Yes. The chi-square test is a statistical tool that allows us to calculate the confidence limits of our MTBF based on the quote-unquote degrees of freedom present in our test data.
Okay, degrees of freedom is one of those textbook terms that makes people's eyes glaze over. Let's ground it. In the context of MTBF testing, the number of degrees of freedom is essentially a measure of how much actual failure data you captured. The standard rule is that the degrees of freedom is simply twice the number of failures you observed.
Correct. If you observe 3 real failures, you have 6 degrees of freedom to work with in your statistical tables. But what happens when you have 0 failures?
2 times 0 is 0.
Right, and you can't have 0 degrees of freedom and still do the math. If the test is time truncated, meaning you just ran it to a predetermined clock limit and stopped without seeing anything break, statistics forces a penalty on you.
A penalty.
Yes, you have to artificially add failures to the math to calculate the lower limit of your MTBF. Specifically, the degrees of freedom is calculated as 2 times the number of failures plus 2. So 2 times 0 is 0 plus 2 is 2.
Why does the math force you to add these phantom failures?
It takes into account the harsh statistical reality that had you kept the test running for just a few more hours or even a few more seconds, that first failure might have finally occurred. You stopped the clock, so you have to assume the worst about what was just around the corner.
Let's walk through the example from our source material to see how brutal this penalty actually is in practice. Consider a manufacturer who builds 100 electronic control units. They put all 100 on a test bench for 50 hours. Total accumulated test time is 5,000 hours. 0 units fail.
Sounds like a great test.
That looks like a massive success. The team wants to declare an MTBF, but they want to state it with a 60% confidence level. They want to be 60% sure the true MTBF is at least a certain number.
Okay, let's do the actual translation of the math. The formula for the lower single-sided confidence limit of MTBF dictates that we take 2 times the total accumulated test time and divide it by a specific chi-square value.
First, we have to find that chi-square value.
Right. Our desired confidence level is 60%. In statistics, our alpha is 1 minus the confidence level, so 1 minus 0.6 gives us an alpha of 0.4. And as we said, because this is a time-truncated test with 0 observed failures, our degrees of freedom is 2.
So we go to our standard chi-square statistical table. We look up the column for an alpha of 0.4, and we drop down to the row for 2 degrees of freedom. The table gives us a value of roughly 1.83.
Now we take that value and apply it to our test data. We take 2 times the total test time, so 2 times 5,000 gives us 10,000. We divide that 10,000 by our chi-square penalty value of 1.83. 10,000 divided by 1.83 gives us an MTBF of roughly 5,464 hours.
I want every engineer listening to pause and let the reality of that math sink in. You tested a massive batch of 100 components. You ran them for 50 hours. Not a single one broke or even hiccup. A perfect run. Your intuition is screaming that this is an incredibly reliable product. But the cold, hard statistics dictate that even at a relatively weak 60% confidence level, you have only legally proven an MTBF of about 5,400 hours. The math essentially took your 10,000 accumulated hours and cut your proven lifespan in half, just to be safe.
It's a massive haircut. And if you change the parameters, the reality gets even harsher. Suppose your massive government contract legally required you to prove an MTBF of 20,000 hours before they cut the check. You run your 5,000-hour zero failure test. What statistical confidence do you actually have that you've met their 20,000-hour requirement?
Oh, wow. We can work the formula backward to find out.
Exactly. You take 2 times the total test time, 10,000, and divide it by the required MTBF of 20,000. That gives you a required chi-square value of 0.5.
So you take the 0.5, you go back to the chi-square table for 2 degrees of freedom, and you find the corresponding alpha is about 0.6. 1 minus 0.6 gives you a confidence level of 40%.
Yes. 40%. You ran a perfect zero failure test, yet statistically, you can only be 40% confident that your product actually meets the 20,000-hour requirement. More likely than not, you haven't met it.
That exposes the absolute illusion of zero failures.
And the incredible danger of small sample sizes. It takes a staggeringly massive amount of accumulated test hours to demonstrate high reliability with high confidence.
Which flows perfectly into the next massive hurdle in reliability engineering: Because since a company cannot afford to run a test bench for 50 years without going bankrupt, how do a manufacturer and a buyer actually sit across a table and agree that a part is reliable?
It's a huge negotiation.
How do you negotiate a test that satisfies both parties? This is the battle between producer risk and consumer risk.
Right. This is the core of fixed-time demonstration tests, and it is a delicate negotiation of statistical exposure. Whenever you test a small sample to judge a massive population, someone is taking a risk.
Let's define the producer's risk first.
The producer's risk is a manufacturer's nightmare. It is the mathematical probability that a perfectly good factory batch of components, a batch that genuinely meets the required MTBF, will just happen to yield a few unlucky, pessimistic samples that fail the test, causing the entire good batch to be unfairly rejected by the buyer.
You built 1,000,000 great pumps, but the 5 you randomly pulled out of the crate for the test bench happen to have minor defects, and the buyer cancels a multi-million-dollar contract.
Exactly. It's devastating. Conversely, the consumer's risk is the buyer's nightmare. It is the probability that a genuinely terrible, defective batch of components happens to yield a deceptively optimistic sample that sails through the test without a hitch, causing the buyer to accept garbage.
You buy 1,000 safety valves that pass the lab test, you install them in your chemical refinery, and they all start failing in a week. To explain how insanely tricky it is to balance these two risks, our source material uses a brilliant analogy. I want to expand on this bad egg scenario because it perfectly illustrates the trap. Let's say you are managing a high-end restaurant, and you consider an acceptable failure rate from your farm supplier to be 1 bad egg in every 10,000. That is the baseline you agree on.
Okay, 1 in 10,000.
To test this quality without breaking every single egg, you decide to randomly sample 6 eggs from the delivery every week. If you get 0 bad eggs in your sample of 6, you pay the supplier and accept the batch.
On the surface, to a layman, it seems like a perfectly reasonable spot check. If the true underlying failure rate is indeed 1 in 10,000, the statistical probability of passing that 6-egg test is incredibly high. It sits at about 99.9%.
So the producer's risk is tiny. The farmer is happy because good eggs will almost always pass.
But let's say a disease hits the farm. The quality plummets overnight. The failure rate skyrockets from 1 in 10,000 to 1 bad egg in every 1,000. The product is now 10 times worse than what you contractually agreed to buy.
What happens to the consumer's risk? You are the restaurant manager. If you calculate the probability of pulling 0 bad eggs in a random sample of 6, when the true reality of the batch is 1 bad egg per 1,000, the math reveals that you will still pass the test over 99% of the time.
That is mind-blowing. The supplier's product degraded by a factor of 10, and your weekly test is still giving them a passing grade 99 times out of 100. You are serving bad eggs to your customers and you don't even know it because your test is blind to the shift in quality.
It's completely blind.
This is the fundamental problem of discrimination in statistical testing. A simple, short-duration zero-failure test on a small sample is a mathematically terrible discriminator. It happily passes excellent batches, but it also happily passes terrible batches. It lacks the statistical resolution to tell the difference.
So how do you fix it?
In order to protect the consumer, to ensure that the probability of acceptance drops sharply the moment the failure rate rises, you cannot rely on a tiny zero-failure sample. You have to vastly increase both the test time and the allowed number of failures.
So to actually catch the drop in egg quality, you can't just test 6 eggs and look for 0 failures. You might have to test 6,000 eggs and mathematically allow for, say, 2 failures to establish a tight confidence interval.
Exactly. You need volume to create discrimination. The source material points out just how punishing this reality is for high-reliability industrial systems.
How punishing are we talking?
Well, if you want to demonstrate a 1-year MTBF with acceptable balanced risks, say, a 10% producer risk of rejecting a good batch, and a 10% consumer risk of accepting a batch that is 3 times worse than promised, you might have to put a single item on a test bench for 3 entire years.
3 years. No engineering firm on Earth has 3 years to test a single component before bringing it to market. By the time the test finishes, the technology would be completely obsolete. Your competitors would have already released 3 new versions. So how do we escape this time trap? Is there a shortcut?
The shortcut is a brilliant statistical method called sequential testing. Instead of rigidly fixing the total test time and the target number of failures in advance, you accumulate test hours dynamically and track the results on a specialized graph.
Okay, how does the graph work?
The graph features 2 parallel diagonal lines stretching upward and to the right. These lines create three distinct zones on the paper: an accept zone at the bottom right, a reject zone at the top left, and a continue testing zone right down the middle between the lines.
Okay, let's visualize this.
Mm.
I'm the tester. I have my graph. I plot accumulated test hours on the horizontal x-axis. Every time the clock ticks, my pen moves to the right. But every time a component actually fails on the bench, my pen steps up 1 unit on the vertical y-axis.
Correct. As long as your jagged plot line stays trapped in that middle corridor between the two parallel boundaries, the math says you don't have enough confidence yet. You must continue testing.
So you just keep running the bench.
Right. However, if your components are incredibly reliable, your pen keeps moving horizontally to the right without stepping up. Eventually, your line crosses the lower diagonal boundary into the accept zone. The moment that happens, you stop the test and accept the batch. You pass early.
Oh, that's great.
And conversely, if the batch is terrible and you get a rapid cluster of failures right out of the gate, your pen shoots vertically, crosses the upper boundary into the reject zone, and you immediately fail the batch and stop testing.
That is incredibly elegant.
Yeah.
It essentially acts as a statistical triage. It saves immense amounts of time, because if a batch is spectacularly good or horrifically bad, the test recognizes the extreme trend quickly and shuts the whole thing down.
Yeah.
You only get stuck in a long, drawn-out test if the batch is borderline and the math genuinely needs more data to decide.
Yes. Decades of military and industrial experience show that sequential testing is significantly faster on average than equivalent fixed-time tests. But, and I must stress this caveat, statistical demonstration of any kind, whether fixed or sequential, can still hit a brick wall of unreality when dealing with truly highly reliable systems.
Like what?
If you are designing a deep-sea submarine valve or a satellite guidance system where the required MTBF is 50 years, you simply cannot demonstrate that statistically in a laboratory environment. The math demands more hours than you have in a human lifetime.
Which raises a very uncomfortable question for anyone managing an engineering team. If you are setting up physical tests for your new product, are you designing tests that actually prove the reliability of your system? Or are you just designing a test that is easy to pass so you can check a compliance box and ship the product?
That's the million-dollar question.
Because if you are just testing 6 eggs, you aren't proving anything. You're just creating a paper shield to hide behind when things break.
That is the harsh reality of the industry. You must understand the operating characteristic curves of your specific test plan to know what level of bad quality you are secretly agreeing to accept. But this entire intense discussion we've just had, chi-square math, the Poisson distribution for zero failures, the parallel lines of sequential testing, every single bit of it has been hiding a massive, glaring, dangerous assumption.
The elephant in the room. Everything we just talked about strictly relies on the assumption that failure rates are constant.
Yes. It assumes that components fail completely randomly, like a lightning strike or the radioactive decay of an isotope. It assumes the part has absolutely no memory of how old it is.
But we live in a physical universe governed by friction and entropy. Things wear out. Rubber seals degrade and crack. Steel bearings lose their lubrication and grind themselves to dust. Aluminum wings experience microscopic metal fatigue every time they flex. A mechanical pump absolutely do not have a constant random failure rate over a 20-year lifespan. It gets physically weaker every single day.
Which shatters the constant failure rate assumption entirely and brings us to the most famous concept in reliability engineering, the bathtub curve.
Ah, the bathtub curve.
If you track the failure rate of a large population of items over their entire lifespan, the resulting graph often looks like a cross-section of a bathtub. At time 0, right off the assembly line, the failure rate is actually quite high, but it rapidly decreases. This downward slope is called infant mortality.
This is the phase where all the manufacturing screw-ups reveal themselves. The bad solder joints, the microscopic cracks in the plastic, the improperly torqued bolts. The parts that were destined to die young fail almost immediately.
Yes. Once those weak links are weeded out of the population, the curve flattens out. You hit the bottom of the bathtub. This is the useful life period. Here, the failure rate is relatively low and, for a time, constant. Failures in this flat zone are genuinely random. A sudden massive power surge, an operator dropping a wrench on the machine, an act of God.
But nothing lasts forever.
No, it doesn't. Eventually, you reach the far side of the bathtub. The curve begins to rise, slowly at first, and then incredibly steeply. This is the wear-out phase.
The physical degradation finally catches up. So, if a failure rate is actively changing over time, decreasing at the start, flat in the middle, and exponentially increasing at the end, How on earth do we model it? Our chi-square equations from earlier are completely useless here because they assume a flat line.
Enter Walody Weibull, a Swedish engineer who, in 1951, presented a mathematical distribution that revolutionized the field. The relationship between failure rate and time can almost always be described by the Weibull formula.
And it's super flexible, right?
It is incredibly versatile because it uses up to 3 flexible parameters to bend and fit almost any shape of data curve. There is the location parameter, denoted by gamma, which simply shifts the entire curve left or right, establishing the starting time 0. There is the scale parameter, denoted by eta, which acts somewhat like an MTBF, stretching or compressing the curve along the time axis. But the absolute star of the show, the parameter that tells you the true story of your component, is the shape parameter.
The shape parameter, denoted by the Greek letter beta, if I understand this correctly, beta is the metric that tells you exactly where you are sitting in the bathtub.
That is the perfect way to visualize it. If you gather your failure data, run the math, and find that your beta equals exactly 1.0, it means your failures are purely random. The failure rate is perfectly constant. The Weibull distribution gracefully mathematically reduces to the simple exponential distribution we used earlier for chi-square. You are sitting safely in the flat bottom of the bathtub.
So logically, if a beta of exactly 1 means a constant rate, what does it mean if beta drops below 1, say 0.5?
If your beta is less than 1, the math is telling you that your failure rate is actively decreasing over time. You are sliding down the left side of the bathtub. You are trapped in the infant mortality phase.
Meaning you have bad parts.
Exactly. Physically, this implies you have severe quality control issues on your manufacturing line. You are shipping defective units. The standard engineering response to a beta less than 1 is to implement a strict factory burn-in period. You run the components in the factory for a week so that all the early failures happen on your time, not the customer's time.
And conversely, if beta is greater than 1.
If beta is greater than 1, your failure rate is increasing. You are climbing the steep right side of the bathtub. Your components are experiencing active wear-out, fatigue, or material degradation.
Okay, so like a gear grinding down.
Right. A beta of, say, 1.5 indicates a slowly increasing failure rate, perhaps due to gradual mechanical wear on a bearing. But a beta of 3.0 or 4.0 indicates a very rapid, highly pronounced wear-out mechanism. It means that almost all of your components are going to survive for a while, and then they are all going to suddenly fail at roughly the exact same age.
Okay, here is where it gets really interesting for the people actually doing the work. Conceptually, beta is brilliant, but practically, how do we actually extract beta from the real world? An engineer has a cardboard box full of broken pumps and a clipboard with a list of the exact dates and times they each failed. How do we turn a list of dates into a viable beta parameter?
Historically, before the era of ubiquitous computing, this was done visually using graphical probability plotting. Engineers used highly specialized double logarithmic graph paper. You plot the cumulative percentage of failures on the y-axis against the time to failure on the x-axis.
There's a massive catch there. You cannot just use raw percentages. If you are testing 10 items and the very first one breaks, you cannot just put a dot at 10%.
Right, because saying 10% of the infinite total population has failed based on a sample size of one failure is mathematically arrogant. You have to adjust for the small sample size.
So you use statistical median ranking tables. These tables provide adjusted percentage values that account for the uncertainty of your specific sample size. Once you look up your adjusted ranks and plot these points on the specialized log Weibull paper, the magic happens.
It really is like magic.
If the underlying physical failure mechanism follows a Weibull distribution, those scattered dots will visually align to form a perfectly straight diagonal line.
And the physical steepness of that line, the slope, is beta.
The slope of the drawn line is exactly your beta parameter.
You can literally measure it with a protractor in some setups. And the point where that drawn line intersects a specific horizontal reference axis gives you eta, your scale parameter. Once you have those two numbers pulled from the paper, you can calculate the true dynamic MTBF and confidently predict the probability of survival for any given hour in the future.
Plotting dots on logarithmic paper with a ruler sounds wonderfully tactile, but we live in the digital age. Nobody's doing this by hand anymore. The source material outlines two primary computer-based methods for curve fitting this data: least squares and maximum likelihood. Want to make sure we don't just gloss over these as magic black boxes.
Yeah, they are very different mathematical approaches. Least squares is the older, simpler computational method. It essentially takes your data points and tries to draw a straight line through them by measuring the horizontal distance from each actual point to the proposed line.
And it squares those distances, right?
Yes, it squares those distance values to remove negative numbers, adds them all up, and adjusts the line until that total sum is as small as possible. It literally minimizes the square of the errors. However, because of how it calculates those distances linearly, it tends to artificially favor the data points that occurred earlier in time.
Meaning an early failure might skew the slope of the line more than a late failure. It's a bit rigid.
It can be very rigid. The vastly more robust and modern method is called maximum likelihood estimation, or MLE. Instead of measuring physical geometry on a graph, MLE looks at the pure statistical probability. The computer algorithm generates millions of hypothetical Weibull lines.
Millions of them.
Millions. For each line, it asks the mathematical question. If this specific line represents the true nature of the universe, what is the exact numerical probability that we would have observed this specific set of broken parts at these exact times? It iterates until it finds the one specific line that maximizes that total probability.
It finds the reality that is most likely to have produced the garbage in your cardboard box. And MLE is particularly crucial because it can handle censored data, right?
Censored data is the lifeblood of real-world reliability. A censored data point represents an item that was part of the test, but did not actually fail by the time the data was collected.
Like maybe the test clock ran out and the part was still humming along.
Exactly. Or maybe a technician accidentally dropped the part and broke it, removing it from the test for a reason completely unrelated to its internal reliability. Least squares struggles with this, but maximum likelihood beautifully factors in the fact that these surviving items existed and endured stress up to a certain point. It gives them credit for surviving, which provides a much more accurate, less pessimistic estimate of true reliability.
So let's tie this back to the engineer's daily life. If I assume a constant failure rate for a mechanical hydraulic pump and I do all my chi-square math and I proudly present a slide to my boss declaring a 5,000-hour MTBF, but the physical reality is that the pump's internal seals are actively degrading, meaning its true Weibull beta is 1.5. My chi-square presentation isn't just slightly off, is it? It is completely dangerously useless.
It is worse than useless. It is a mathematical lie that will cost the company millions. You used a statistical tool designed to predict random lightning strikes to model a system that is bleeding to death from 1,000 cuts. Your chi-square calculation assumes that the pump is just as healthy and robust at hour 4,000 as it was at hour 1.
But it's not.
Not at all. A true beta of 1.5 guarantees that the pump is vastly more fragile and likely to fail at hour 4,000 because the seals have been wearing away every single day.
You are blind to the wear out because you chose the wrong equation. This perfectly highlights why understanding the physical failure modes is infinitely more critical than just crunching numbers in a vacuum. Which leads us to one of the most fascinating counterintuitive traps in all of engineering analysis. This is where data actively lies to you if you don't understand the physical context. Let's explore the continuous process illusion.
This phenomenon is a trap that catches even seasoned reliability veterans. It is a phenomenal example of how an entire system can camouflage its true nature.
To explain this, we have to look at the filament lamp example from the text. Light bulbs. Let's scale it up to make it vivid. Imagine we construct a massive, state-of-the-art skyscraper. On opening day, we install 10,000 identical, brand-new light bulbs throughout the ceilings.
Okay, 10,000 bulbs.
Now, we know from basic physics that an incandescent light bulb does not fail randomly. It has a very distinct, well-documented wear-out characteristic. The tungsten filament literally burns away over time. Its Weibull beta is usually well in excess of 2.0.
Correct. A light bulb is a textbook wear-out item. They all survive for a very predictable long period of time. Then, as the filaments thin out and become fragile, they start failing very rapidly, clustered tightly around their design life limit.
So in our new skyscraper, for the first few months, it's smooth sailing. The maintenance crew is bored, maybe a handful of defective bulbs burn out early infant mortality. But as we approach the one-year mark, suddenly, it's an absolute bloodbath.
The wear-out hits.
Exactly. Bulbs are burning out by the hundreds every single day. The maintenance team is running ragged with ladders. If you plotted the failure distribution of that original batch, it would look like a massive, steep bell curve localized right around that one-year wear-out age.
But here's where the illusion takes hold. The skyscraper doesn't stay dark. Every single time a bulb burns out, a maintenance worker immediately replaces it with a brand new one. Fast forward 3 or 4 years into the future. The building no longer contains 10,000 bulbs of the exact same age.
Right, because of the constant staggered replacements.
Yes. The building now contains 10,000 bulbs of wildly different ages, forming a completely homogenized mixture from brand new to nearly dead.
So what happens to the failure rate of the building as a whole macro system?
Because the individual bulb ages are completely randomized across the ceilings, the number of bulbs failing in any given week stabilizes. It becomes approximately constant. 50 bulbs fail in January, 48 fail in February, 52 fail in March.
To the building manager sitting in the basement looking at a spreadsheet of weekly maintenance expenses, it looks exactly like a constant failure rate. The failures appear completely random and evenly distributed over time.
And that is the terrifying part. A population of physical items governed by a strongly increasing failure rate, a massive wear-out mechanism suddenly appears to the macro observer as a constant random failure rate system. If a new reliability engineer came into that building, recorded the time intervals between maintenance calls, and ran a Y-bowl analysis on that mixed data, the computer would spit out a beta of exactly 1.0.
The engineer would look at the math and happily conclude, light bulbs fail purely randomly. They don't wear out. Which we know is a physical absurdity that violates the laws of thermodynamics.
This is exactly why I constantly warn teams. You must separate your failure modes, and you must ruthlessly track individual item histories from their specific time zero, not just track system-level alarms.
It's about data hygiene.
Yes. If a factory manager is replacing rubber pump diaphragms during routine maintenance, and the tech just scribbles "diaphragm failed on Tuesday" in the logbook without recording the exact serial number and installation date of the previous diaphragm, the data is poisoned.
The manager can never run a Y-bowl analysis to see if the rubber is degrading prematurely, because the timeline is just broken.
The data is hopelessly mixed. The manager will just see a steady, constant trickle of failures on the line and falsely assume it is a random, unavoidable fact of life. To do real, actionable reliability analysis, you must preserve data hygiene. You need the unique identity of the item, its exact operational time to failure, or its exact accumulated time of replacement if it survived. Without that granular discipline, statistical analysis isn't just impossible, it is actively misleading.
Okay, we have covered a staggering amount of ground today. We tore down the illusion of precision in the databases and exposed the variables hiding in the margins. We navigated the arithmetic mean trap, we shattered the zero failure fallacy, and felt the sting of the chi-square penalty. We explored the brutal reality of producer and consumer risks using bad eggs, and we used the Weibull distribution to respect the physical reality of the bathtub curve. And finally, we uncovered how wear-out disguises itself as randomness. Which brings us to the ultimate question. How do we turn this mountain of theory into a step-by-step practical approach? How do we actually optimize a design, and why do our paper predictions so rarely match the messy reality of the field?
This is where we distill everything into an actionable philosophy for the drafting table. Step 1 is acknowledging the databases for what they are. Use Faradip, use MIL 217, but respect their extreme limits. Never take an arithmetic average of extremes. Use the geometric mean to establish a mathematically credible baseline that balances the orders of magnitude. Then, apply your environmental multipliers thoughtfully, but always treat this final baseline number as a relative indicator of approximate capability, not a legally binding contract with the universe.
Step 2 is defining your failure modes. This is arguably the most important physical step. The source material hammers home the point that predicting a single, monolithic total failure rate is largely useless if you don't know how the system is failing.
Exactly. Let's look at a critical safety shutdown valve in a chemical plant. The database prediction says it will fail once every 5 years. That number alone tells you nothing about risk. If 90% of those predicted failures manifest as spurious trips, meaning the valve accidentally triggers and safely shuts down the plant when there is no actual emergency that is annoying, it costs the company money and lost production, but nobody's injured. The system failed safely.
But if 90% of those failures manifest as a failure to respond, meaning the reactor is overheating, the alarm is blaring, and the valve is physically jammed open, that is catastrophic. The plant explodes, the system failed dangerously.
The total baseline failure rate is exactly the same in both scenarios, but the real-world impact is vastly different. This is why you must perform a rigorous failure mode and effects analysis, or FMEA. You have to take that total failure rate and mathematically apportion it into specific physical modes. Short circuit, fail to release, blocked port, spurious trip. Only by dividing the risk can you design the correct protective architecture.
Step 3. Use your failure rates for relative comparisons, not absolute promises. If we accept everything we've talked about today, that failure rates are perhaps the least precise engineering parameter in existence, subject to massive hidden variables, what good is the final MTBF number on the datasheet?
It is an architectural design tool. You do not look at a predicted MTBF of 50,000 hours and promise the client 50,000 hours. You use that calculated prediction to make internal engineering decisions. You compare design prototype A against design prototype B. You ask the math, if I spend the budget to add a redundant cooling pump to this subsystem, how much does the overall system availability improve relative to the original design? The absolute numbers on the paper might be off by a factor of 3 compared to reality, but the relative percentage contribution of each part to the total system risk is usually quite accurate.
It acts as an X-ray. It highlights where the fragile bones are, even if it can't tell you the exact date the bone will snap. It guides your redundancy and architecture decisions.
It forces you to allocate your budget where it actually matters. And finally, step 4. You must realize where the true benefit of reliability engineering actually lives.
Didn't live in the upfront paper prediction, does it? The prediction is just buying a ticket to the game.
The primary benefit is reliability growth. It is everything that happens after the system hits the field. It is the relentless continuing analysis. It is meticulously tracking the field data, maintaining perfect data hygiene so you can run a proper Weibull analysis, realizing your pump's beta is actually 1.5, performing a physical root cause analysis on the degraded seals, and issuing a design change to use a different polymer in the next manufacturing run. True, practical optimization is an endless feedback loop of design, testing, field data collection, and corrective action. The initial paper prediction just gets you into the ballpark. Growth wins the game.
So, to synthesize this entire journey for the engineer listening, we avoid the trap of the arithmetic mean because it maliciously biases toward the worst-case scenario. We rely on the geometric mean to respect logarithmic variance. We never, ever fall for the intoxicating zero failure fallacy because we know chi-square proves that small sample sizes with zero failures only guarantee mediocre, heavily penalized reliability. We deeply respect the producer and consumer risks inherent in any physical test, recognizing that demonstrating high reliability requires either impossible amounts of time or clever sequential testing. And we use the Weibull distribution to honor the physical reality of the bathtub curve, ensuring we never treat a grinding, wearing gear like a random bolt of lightning.
That is the comprehensive, mature approach to the discipline. It requires abandoning the warm comfort of binary pass-fail engineering and fully embracing the nuanced, often uncomfortable reality of statistical confidence.
This has been an incredibly deep dive. I feel like we have fundamentally dismantled and rewired how we look at MTBF data sheets and testing protocols. But before we sign off, I want to leave the listener with a final thought, a provocation to mull over based on everything we've unpacked today.
We've clearly established today that failure rates are the least precise parameter in our toolkit, and that statistically demonstrating high reliability for critical systems is nearly impossible within a reasonable time frame or budget. This raises a profound structural question for our industry. Are our rigid contractual reliability requirements actually stifling true technological innovation? If massive organizations demand absolute statistical certainty, forcing engineers to mathematically prove decades of MTBF on paper before a new system ever sees the light of day, are we just forcing teams to design for the test rather than designing for reality? Are we trapping ourselves in a cycle of using conservative, heavy legacy designs just because they have historical database entries, while actively ignoring superior, innovative designs simply because they lack the millions of accumulated test hours required to appease the chi-square penalty?
That is a brilliant, unsettling point to end on. Designing for the test versus designing for reality. The friction between innovation and statistical fear. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.